This opening slide maps the simple journey of NPUs, from lab concepts to everyday laptops, showing how ideas move from prototype benches through R&D and commercialization before landing in consumer devices. And the diagram helps us visualize that pipeline so we can keep the big picture in mind as we dive deeper. This timeline traces how university prototypes and sparse, near-eye memory designs sparked startup evangelism, which then led to a consumer breakthrough with mobile NPUs and finally broad industry adoption. The slide shows early demos, Apple's A11 as a milestone, and how semiconductor giants eventually embraced the commercial case. Here we look inside NPU architecture and why it's efficient. Thousands of INT8, 516 Max tuned for high utilization, on-chip SRAM for weight reuse, and lean control logic, all combining to deliver roughly 3 to 5 times better energy efficiency on transformer and CNN workloads, and enabling continuous background AI without active cooling. Raw TOPS are just a marketing metric, and real NPU throughput depends on memory bandwidth, quantization tools, and optimized drivers. The right middleware and unified SDK layers, as shown here, turn theoretical performance into usable developer assets and dramatically reduce porting time across Qualcomm, Intel, AMD, and other stacks. This market snapshot shows why NPUs matter commercially. 1 billion edge devices, a laptop baseline around 40 TOPS, automotive systems demanding over 200 TOPS, and even IoT voice activation at about 5 TOPS, all feeding a rapidly growing silicon revenue pool currently measured in the tens of billions and outpacing CPU and GPU segments. NPUs unlock real user and business benefits, from recall-style semantic search, live video relighting and private on-device LLM copilots, to automotive vision stacks, factory defect detection, point-of-care imaging, and retail loss prevention. And these use cases translate into tangible ROI, like lower cloud bills, better privacy, and offline reliability. The ecosystem slide highlights a core barrier: fragmentation from vendor-specific ISAs, missing CUDA-style universality, and repeated model rebuilds, which inflate QA costs and slow software roadmaps. The consequence is higher development overhead and a real risk that NPUs get relegated unless we embrace shared standards and tooling. This memory wall slide explains a growing tension. Model parameters are exploding while on-chip SRAM and bandwidth grow slowly, forcing solutions like distillation, sparse inference, and compute in memory. Yet physics means some workloads stay cloud-bound, so the industry must balance what stays local versus what streams remotely. Looking ahead, spiking arrays and memristor crossbars promise to upend the von Neumann bottleneck by doing in-memory compute and cutting data shuttling, potentially delivering huge power savings. Early 2025 prototypes show promising TOPS SOL per watt, with some accuracy trade-offs to close, but an outlook that could leapfrog conventional approaches over the decade. Tomorrow's processors will be tightly heterogeneous, combining CPU, GPU, NPU, and FPGA, with cache-coherent memory, chiplet scaling, and AI-aware schedulers, so real-time graph migration and orchestration become possible, enabling foundation models on every device, while shrinking board area and delivering workstation-class AI in very low-power envelopes. The strategic imperatives slide boils down to 5 priorities: optimize memory bandwidth and quantization first, invest equally in SDKs and software parity, push for standardization, embrace hybrid architectures for real workloads, and pursue continuous co-I design between models and hardware, all emphasizing efficiency value over raw TOPS claims. Finally, 2025 looks like a tipping point. A new 40 TOPS entry-level, meaningful NPU revenue versus flash memory, and a fork in the road where neuromorphic research, 3D chiplet stacks, and open ISA efforts will decide whether we end up with ubiquitous neural fabric or a collection of siloed accelerators with niche roles.